My name is Chris McCall. I'm director of the CERN and Earth and Space Center at Triton College. We're glad to have you all here tonight. Of course, we would much rather have you in the planetarium for this CAS meeting, but since we can't do that, we're happy to host. And feel free to, if you have questions, even during the talk, you can type into the chat box if you don't want to interrupt. What we'll also try to do is we'll watch the chat box, and if it's a question, we might jump in and interrupt you, Tom, if we think that it's advantageous to address it right then and there.
Yeah, you're cool, no problem.
So, like I said, feel free to type into the chat box, be nice to everybody else. And James Kuka, I'm going to let you talk about CAS and about our guest tonight.
Okay, well, this is, I guess, this is the August meeting of the Chicago Astronomical Society. I want to thank Chris and the CERN and Earth and Space Center for hosting this Zoom. And our speaker is Tom Field, who is a contributing editor to Sky and Telescope magazine. He is the author of RSpec software, and he has spoken to numerous astronomical societies and conferences. And tonight, Tom is going to talk to us about spectroscopy. He's going to tell us what it's all about, and what I find most intriguing is how amateur astronomers like us can actually get involved. Apparently, you don't need, you know, a huge budget with big telescopes. And Tom, if you could just take it away.
Good. Thank you, Jim, for the invitation. And also thanks for doing the work to make this all happen. You and I initially communicated a handful of times to get all the schedules set up. One quick thing for those of you who aren't all that familiar with whatever we're on Zoom here. If you're seeing me in a big picture in the middle of your screen and just a handful of video and names across the top, in the upper right-hand corner of your screen is a button that's got that icon on it. It also may have the words gallery view. If you click that, you'll see it's a toggle switch. If you click that, you'll see everybody here that fits on the screen, and maybe during the Q&A, people will turn their video on so that we can see their faces. So that's just a nice trick. I don't know why Zoom starts out meetings with that sort of focused view on the speaker. I suppose having a big head in the center of the screen is easier to follow. I think it's much easier or much more fun from a social standpoint to be able to see everybody. All right, so I'm going to share my screen here and do this. There we go. Can you see that prism there, Wayne? You're going to be my guide here. You can shake your head, yeah. And then maybe you can mute all the speakers and then unmute me, or I can unmute myself. So I'm going to talk for 45, 50 minutes. We've got a lot of material to cover, and then we'll do a Q&A. You're going to actually have to drag me off the stage. So if you've got questions, I'd love to hear answers. I'll give you or give answers or try to. And I'll give you a little bit of my history as we move on through the presentation tonight. So how is it actually that we've managed to discover so much about the universe when we haven't left home, right? We haven't even gone out the door. Images, of course, can show us 2 dimensions. And one interesting thing about this Hubble Deep Field, this is a piece of the sky the size of a tennis ball held at arm's length. Such a tiny little piece. There's so much up there if you can get outside the atmosphere with a big telescope. And we, of course, can get fleeting glimpses of a 3rd dimension if we see an eclipse. And if we wait a while, we can see, you know, some stars going on and off, a 4th dimension time. These are on and off relatively anyway. These are some standard candles that we use, and they reveal something about distance and time. And if we spread the colors out, we get an as-if 5th dimension. And this is a barcode-like image that helps us understand a lot about stars. Not only what they're made of, and we're going to talk about this, and I'll give you examples of all these this evening. Again, if they have any radial velocity towards or away from us, if the star or galaxy or even planet is spinning, what its temperature is, where it is on the HR diagram, and even its distance on some occasions. So, like I said, I'll give examples of these. Now, this screen has more words on it than any screen you'll see tonight, but as I've given these talks, I've realized that there's some key points that I'm trying to communicate, and I thought I'd just start out and just lay them out here so you know what you're in for. So you might want to capture star spectra if you remember the thrill of that first image you took of the moon. For those of you who are imagers, I'm not a big imager, but I did capture the moon. It was blurry, it was overexposed, but it was the most beautiful image I'd ever seen, right? And you may have had the same experience. I showed it to my wife and my friends, took it to work. So, but that thrill fades after a while. And I found when I got into spectroscopy, I got that thrill back again. It was really very exciting to me. Maybe you want to do some science. That's why I actually got into this. Maybe you want to contribute to professional amateur collaboration. You know, my wife, she's, we call her, or she calls me, either way, the credit card scrutineer. I don't like making big investments into new things I don't know much about. I don't know if I'm going to like, and you're going to see that it's really easy to get started doing the things tonight. Now, I think this is the most significant point here, and that is when you actually own the data, you get much more interested in understanding it. And so I find as people send me things or I observe things myself that are spectra, I'll go out to Wikipedia, I'll read a little bit. Look, I am not a scientist. I'm a very broad river, but I'm really shallow. So in the Q&A, we'll expose that a little bit perhaps. And spectroscopy isn't nearly as dependent on dark skies. And so a lot of people do it in their driveways. And thank goodness you don't need a PhD in astrophysics. I think one of the obstacles to people getting involved is they think, I'll never understand this. And believe me, if a knuckle-dragging programmer like I can understand it, so can you. You don't have to know a lot, and there's lots of help out there, and I'll show you some of those sources. I'm not a big imager. I don't have the equipment, patience, time, or really interest. I'm glad some people do. But you're going to see some images shot in video in quarter-second frames tonight. And I break just about everything I touch. Maybe you're that way too. I think, in fact, my favorite command in Windows is Edit Undo or Control-Z. Sometimes, on rare occasions, though, thankfully, I wish there was an Edit Undo in life, you know. But what I'm going to show you tonight is not a do-it-yourselfer project. If you do any outreach, you want to do some mentoring, this is a really cool aspect of astronomy. It's real science, and it often wins science fairs for high school kids. And this somewhat tongue-in-cheek, I assure you, I'm not part of the cool crowd, but there are 10,000 amateurs doing this today. This isn't some esoteric branch field that I'm flogging here. You'll see a lot of different people, examples as we go through tonight. So real quickly, we're going to look at a little of the history and a little of the science. It's unavoidable. Some of you are familiar with all this, but we want to really get everybody to a similar level so that what we're going to talk about makes sense. Of course, Newton discovered that with just a simple prism, we could split light into the rainbow, and we can also just bounce it off a finely lined surface or even through a finely lined surface and get the rainbow as we see on that DVD there. Fraunhofer's credited about, 200 years ago now with inventing the spectrometer and observing the first spectra of stars. But Bunsen in the 1850s really was the first big name that was still remembered, because he invented the Bunsen burner to burn things, look at their light through a prism, and through those observations, he recorded everything that he saw, and those records really came in handy, as we'll see in a few minutes. One interesting thing about Bunsen is he deliberately did not patent the Bunsen burner. He said this should be available for humanity, for anybody who wants to further the good fortune of humanity with science. Today, there'd be 20 patents on that little device for sure. So Kirchhoff over on the right there, he was a co-researcher. We're not going to get into a lot of depth on him, but I wanted to mention his name because there is one thing which we'll look at really briefly, and that is, notice this spectrum here, right? It's a rainbow in Roy G. Biv order, right? Red, orange, yellow, green, blue, indigo, violet, and it's got gaps in it. But notice there's another spectrum down here that's all black with just some colors. Which one of those that you get depends on the temperature of the gas on the star and you know, a lot of other factors, shall we say. And we're not going to talk about those, but what I wanted to mention was that regardless of whether it's an absorption or emission spectrum, you can see that the lines are in the same position. And so we'll see examples of both those kinds of spectra as we go through examples tonight. So here's an example that shows that each element has its own fingerprint spectrum. You can see there, for example, the hydrogen at the top doesn't have a corresponding absorption line down here in helium. And in fact, the hydrogen is so commonly used that we've named its gaps, or lines, they call them, the hydrogen bomber lines, or the hydrogen bomber series, and even given them names, Greek names, like we give to the constellation stars, alpha, beta, gamma. You're going to hear about them a lot in the next few minutes. So here we can see really briefly that there's hydrogen, and there you can see its spectra there's a hydrogen alpha, hydrogen beta, hydrogen gamma. That's that fingerprint I mentioned. Notice how different helium is. And even different, for example, here, lithium, which is, you know, in your cell phone battery or in your laptop battery. Very different spectra. And that's how we use these spectra, because they're unique. Now, these days, we don't have to burn anything. You can see there on the left, there's a gas tube. And it's just like a fluorescent tube. I've got one over here, for example. I can just turn on to show you. It's just, you know, it's a glass tube with some metal contacts on the end. And now that Bunsen's done the research, and over the years others have cataloged all the different elements, gas tubes, we don't even need to use those all that often. So we developed, for people who teach, we developed a little turnkey spectrometer for the classroom labs, physics, chemistry, astronomy, and have done a lot of work with universities and high schools in that. So in 1835, we're going to jump around a little bit time-wise. I'm moving fast through this because I know it's just the boring history. Auguste Comte said, the stars are too far away to observe. But several decades later, a variety of people in Italy, in the UK, and France were observing the spectra of stars and using some of these spectra that Bunsen had captured to identify some of the composition of stars. Now, so far, every example I've given have been an old white man. And so I've got some up here, women astronomers, who I think, some of whom you may know of, but I think it's important to recognize the opportunities that didn't exist and the great accomplishments in spite of that. So Annie Jump Cannon and her team of computers were prohibited from using the telescopes because of their gender. So they studied the glass plates, the film plates of spectra, and through a lot of hard work and ingenuity and brightness, they came up with a classification system for the stars. Priyamvada Nataraja is at Yale, and she studies black holes. Nancy Grace Roman just had a telescope that's being named after her. She was the first astronomer at NASA, got her PhD in the late 40s, was instrumental. The Hubble Space Telescope was her vision, and she made it happen. Elisa Quintana studies exoplanets and discovered some exoplanets around red giants in the Goldilocks region that's not too close or far away, so they could have liquid water and perhaps life. And Jedediah Eisler is at Dartmouth, and she studies hyperactive black holes and gravitational lensing. So this is a relatively new slide for me, and it was, as I was researching it, it was like, you know, falling down a rabbit hole, because there are so many women out there who have done and are doing just fantastic work in astronomy. The opportunities are opening up, but we still have a long way to go. So again, this may be familiar to a lot of you. How do we get these fingerprint emission and absorption lines? Well, the Bohr model of the atom has, and this is a hydrogen atom, has multiple concentric orbits, and the electrons sit in those orbits, and when they jump, they emit or they collect energy, absorb. And so there is a hydrogen gamma line. Sometimes that energy is in the visible portion of the spectrum. So here, for example, when an electron sitting here jumps from shell 4 to shell 2, when it jumps down, it emits what we call the hydrogen beta line at that wavelength. When it jumps up, it absorbs that energy, and we have a gap. So we're going to see examples of these in the next few minutes. Some examples of some of the professional spectrographs. The one on the right is in southern France, discovered the first exoplanet. There's an amateur star party for spectroscopy there. And when things open up again, maybe next summer, it's a wonderful opportunity to go on a neat trip, stay in a little bed and breakfast in southern France with your spouse or friend, and eat fresh croissants and meet a lot of amateurs doing this kind of thing. The space shuttle serviced the Hubble spectrograph in this photograph. Now, my teenage grandson says that that's not a scientific instrument. He says that's a refrigerator and that it's filled with beer and that they're real party animals every night. Of course, they have a lot of nights on the space shuttle. They did have a lot of nights when it was flying. And so he says, like I said, they're real party animals up there. Let's leave that. Here's an amateur device. You can see it looks rather complicated and expensive. What I like about this slide is this little fluorescent light here, some sort of gas tube. See the two little pins there? And I pictured Dale. I think he regrets ever having allowed me to use this photograph, because now thousands of people have seen his setup. What a rat's nest. Picture him with two alligator clips, high voltage, clipping onto those little pins. I mean, it's bad enough that he could shock himself, but the worst thing is if he draws a spark, he's going to ruin his night vision, right? Okay, so you don't need a complicated setup, and that's most of the examples I'm going to show you tonight are using just this $200 star analyzer grating. It's mounted in an 1.25 inch filter cell. And here's our first example. You can see there, it's just threaded onto the lens cap threads of a DSLR. And there is our hydrogen alpha, beta, and gamma. Now, you'll notice there's also no tracking on this. That makes it considerably harder, as well as the small aperture of a DSLR. So it's not an easy way to go about things, but I show you this just so you see how simple it is. It can be done just with a common off-the-shelf DSLR. So in the upper left here is that DSLR again. And the reason I wanted to show you this here is just to point out, if I can get my arrow working, point out that adapter there, which we sell, that adapts the filter cap threads on the DSLR to the 1.25 inch threads for the grating itself. But you don't need a DSLR. You don't need a color camera. Here's a cooled FITS camera. It can be mono. Here we've got a video camera. This is actually an imaging source video camera, and we'll see some examples from that kind of camera, and you can mount it inside a filter wheel. So there's lots of ways to mount these things. There are more expensive devices, and I'll show you examples of spectra from these and why they're superior, but you can see they're an order of magnitude not only more expensive, but considerably more difficult to use because they have a slit. They have a slit that's about 20 microns across, which means you've got to acquire your target and track on a 20 micron slit. So again, it's a higher resolution, and you'll see how that comes into play. Here's an example of the star analyzer on a DSLR piggybacked, and then down at the bottom you can see is a more high-end device. There's also a do-it-yourself 3D printed device that the parts are about $500 now, if that's your cup of tea. Okay, we got all that behind us. Now let's talk about what we can actually do and get into the meat of things. So you take a star, you put the light through a grating, you get a spectrum. Here's our first example. This is done by a guy in Europe named Torsten Hansen. And you can see there's his name down there. And up on the top, you can see it was like an 8-inch Newtonian and an imaging source DSLR, or video camera. So here you can see different spectra. These are captured at different times, and they're in temperature order. So the hot stars, the B stars are up here. The cool type M stars are down here. Look at those differences. Just right out of the gate, without really doing anything numeric, we can see very big differences between the stars. For example, and we'll look at two examples here. Notice these bands down here. Well, these cool type M and to some degree K stars in the cool end, their outer shell is cool enough that a more complex molecule, titanium oxide in this case, and I couldn't tell you anything more about it than that, can survive. The other example I want to show you, so when you see these bands, that means, hey, we've got a cool star. But the other example I wanted to show you is this one right here, and that's right around 4800. That's our hydrogen beta that I mentioned earlier. And you'll notice that this particular, if I can find my mouse here, this particular gap is broader and darker on this type A star. Now remember this, you may not remember, and I didn't remember it even after giving this talk a lot until a couple of days ago when I thought, this is probably important to say. This particular gap is caused by the electron jumping from level 4 to 2 or 2 to 4. And in that case, on the hotter stars above it, on these stars, notice it's not as strong because these stars are too hot. So the electrons don't even, a lot of them don't even end at level 4. They just keep going up to level 5 and 6 and above. And the same thing similarly with these cooler stars, these type F and then K and M stars, is they're not hot enough to pump enough electrons up to that level 4. So now we're determining star temperature with a simple video camera. So, but I'm going to put some crosshairs up there, and I hope you can see that right in the crosshairs. You probably can't, but there's a little bit of dimming in there. Well, you know, I can't submit a paper. Suppose I had access to the Hubble telescope, and I tried to submit a paper and said, you know, we used the Hubble, we studied this, and we saw a little dimming in like the robin egg blue. That paper would never be accepted, right? That's not science. So to quantify this, we need to actually get some numbers, and we do that by graphing it. Now this is pretty straightforward. The star is bright and narrow, so this peak, this is an intensity curve here, this peak is tall and narrow, and this is narrow and dim and gets brighter and then gets dimmer again as we move from left to right. So that's what happens here: brighter, 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 dimmer, dimmer, dimmer. And the cool thing is now we can see that gap in the robin egg blue really clearly. Now we can measure its depth, full width, half maximum. Where is it located? How does it compare tomorrow with tomorrow's view of the star? If it's a variable star, a changing star, how does it compare to other stars? That's science. Now, how do we get this graph? So my story is I wanted to do some science, and I got a grading. I put it on my C8 here, 3 miles from Pike Place Market in Seattle, in my backyard, right out that window in 2009. Came in at midnight one Saturday night, grass stains all over my blue jeans because it was Vega, and you know what Vega's like in the summer. So Sunday morning, I tried to get this graph and I couldn't. There is freeware out there, but the freeware was just so frustrating to me. It was in French, it was crashing. It wasn't really designed to the level of user interface and usage that we've become accustomed to over the last 2 or 3 decades. I gave up. Honestly, I quit. I told my wife, I'm supposed to be having fun, and this isn't fun. I bit off more than I care to chew. But I actually threw it in the drawer. I guess if I had a visual aid, I could show you. There's the box. I put it in, and I just threw it in the drawer. But it kept bugging me. I wanted to do it. So a couple weeks later, I sat down one Saturday, and I wrote a program just to create this graph. I figured, great, that's all I want. Sunday, I had a graphing program running. Now, 10, 11 years later, and 10 or 15,000 hours later, the program is almost done. My wife keeps asking, when's it going to be done? I want to start having dinner at regular hours, regularly. And it's done. I mean, lots of people have it, but there's always room for improvement. I want to show you that for about 2 minutes. It's not a software demo. It's too late at night. All of you would be sleeping. You know, you'd be nodding off, hitting your heads on your microphones. But I do want to show you the program because I think one of the obstacles to doing this kind of thing is also, well, how am I going to learn? I don't want to learn another software. It's a steep learning curve. Well, so here's an image from my Fitz camera. It could be a frame from a video. It could be a DSLR image. I prefer color for educational purposes. Mono is going to be more sensitive. There's the star, there's the spectrum, there's a gap there where my mouse is and some gaps there. So once I have an image, and this could be out under the telescope, I just bracket in the star and its spectrum like this, the area I want to study, and I've got the graph. So this is the intensity peak for the star, and this here is that data. So that gap right there is that dip right there. Pretty cool. So now we're actually ready to do some science. And let me drag some things around here. Can you see me changing anything on my screen? Wendy, I can see you. Nod your head. Is anything changing right now? Hard to say. Okay. So I'm trying to get to, oh, I know what I have to do. There we go. I wanted to show you this filled because that now we're getting into something that actually looks pretty interesting when you're doing outreach. And even more exciting, this is a video. That was a freeze frame from the video. So the image is changing here, so this is jumping around. Now, what about all those dips? Oh, and we can turn on stacking. in the software. Watch it stabilize. The dips get deeper and steadier. But what about all those dips? Another obstacle to getting involved in this is, as I said earlier, I don't have a PhD. How do I know what dip is what? Remember, I mentioned that Bunsen created this catalog of all the elements that he burnt and where those absorption or emission lines would be. Well, we have that catalog built into the software. So I can come down here to Hydrogen Bomber and say, show me on the graph where those absorption lines are. Where would we expect to find hydrogen alpha on our data if it was there? And wow, we've got it going right through that dip. We've got that going right through. So what we've done here is fairly conclusively demonstrate with a backyard telescope, first time out, this is my first spectrum, that this star is composed of at least a lot of hydrogen. That's pretty amazing. Could be, you know, millions of light years away. So that's all I want to show you here, except I'd like you to just remember in your mind's eye, it won't be a quiz, but I'm going to show you this view here in a little while with these hydrogen lines, and also this is Vega with these curves and these features to show you how some research gets done. So hang in there, and let's move on back to the show here. Here's an outreach, for example, projected on an overhead screen. This is actually a gas tube spectra they're starting with. This is in Marseille, France. I love this image because clearly they've got a crowd. So here's an image, a little bit wider view with a DSLR. You can see down here, here's a Wolf-Rayet star. There's some emission lines there, and we'll talk about that in just a moment. Here's another pair of stars, and here's a spectrum with some gaps. So it's a beautiful view. So when Janet Simpson sent me this spectrum some years ago, I have a confession to make to the group tonight. I couldn't remember what a Wolf-Rayet star was. And you may have gone through the same thing. Things go in one ear and out the other, especially as we get older. Wikipedia is our friend. Wolf-Rayet star are massive stars. Late in their lives, the outer shells have somewhat dissipated, and we can see down towards the core. This is what the spectrum looked like from her image. And what we're seeing here is carbon. Now remember, stars burn their way through the elements, and they step up from hydrogen to helium and so forth, and now we're up to carbon. So we're sort of seeing the soot in this star. It's really amazing that we can do that with a DSLR and just a mechanical tracker. So, but let's look at our beloved Ring Nebula with the star analyzer grading. Not so interesting. See, without a slit, you actually see the original arc target repeated all the way across the spectrum. Now, this is an emission object, and there's really only two colors in it, so it's interesting. But most objects aren't interesting if they're extended without a slit. But let's look at a slit example of an extended object. Here's the Orion Nebula. And again, I didn't call them out in the previous screen, I forgot to, but same elements. Now, this is early stage, not late stage. But here we can see really narrow, nice, easy to spot lines, even though it's an extended object, because this is done with one of those slit spectrometers. So I'm going to stop sharing my screen just for one moment here, because this is a good point to just ask the group, if any of you care to, you can just unmute yourselves, just to tell us if you remember, and if nobody volunteers, that's cool too. I'm not going to put anybody on the spot. The first time that you saw the Orion Nebula, where were you? What kind of telescope were you using? And what did it look like to you? What was your experience? Anybody want to volunteer? You can just unmute yourself. Bueller? Anyone? Anyone? Boy, don't jump all at once. At least I got one smile. Somebody got the joke. Okay, so now you're going to be stuck hearing my story, which is not all that time intensive, but I bet you it's not dissimilar to some of yours. And that is, I was going out, it was the early 90s, first time out at a star party in Denver, downtown. And it's fun to remember when you didn't know something and how you can misunderstand things. It's not often we can remember back. I mean, imagine before you had all the words that you have today, you know, when you were 3 years old. So I remember walking out onto the observing field, and what I saw to my uneducated eyes, you know those cannons in the circus that they shoot people out of? That's what I saw. I saw tons, and I'm thinking, what are they doing with these circus cannons? Of course, they were Dobbs, but I didn't know any better. I queued up at a Dobb. There was somebody like many of you manning the telescope, womaning the telescope. And by the way, earlier on, there were more women in this meeting than men. which is a really wonderful accomplishment. Welcome, everybody. So the person at the telescope was running, it was all excited, you know, a stellar nursery, all that. I got up and looked through the eyepiece and I was really disappointed. It was a smudge, it was nothing. You know, you probably had the same experience, but here's the deal. I still go back, and you do too, I bet, sometimes look at M42. Why would I do that if it was so boring? Well, two reasons. First of all, you know, we've gotten better at averted vision, right? We can now, you know, look out of the corner of our eyes and you know, see more detail. But more importantly, we understand what we're looking at. And we bring that understanding to the eyepiece or our visual imaging. And when we do that, we get a much deeper experience. And the reason I tell you that story is, as I've captured spectra and read a little bit on Wikipedia or had somebody explain to me what I was seeing, I found that my enjoyment of visual observing deepened too, because I understood more and it remained intact. I didn't forget it. Because again, I had that data in hand, and so it became more interesting. So let me move on to the next slide. So here's an example done with a video camera at 4 frames per second. That's the spectrum of Uranus and Neptune. Look at those gaps there, which are the methane. We're detecting methane on these planets. Now these, again, they're not point source, but practically so, right? You can't do this without a slit on Saturn and Jupiter or Venus, because they're too extended. But it's possible. Imagine professional astronomers, if you told them in their backyard with an 8-inch telescope that they could have captured the atmosphere of a planet. Here's our showpiece, Albireo, and I just show this slide to point out that the blue star has more of its energy. See how much higher the curve is through here in the blue end, and the cooler yellow star has more energy over here in the cool red end. So in 1881, you can see at the bottom there, Henry Draper observed a comet. Hank, if Hank can do it, so can we. So here's the spectrum of a comet, and you can see it's beautiful little string of gems here in the spectrum, and there are the peaks from it in the plot, called a profile, by the way, and those are the swan bands. Now, you might be thinking, wait, Tom, a minute ago you said you can't observe extended objects with just a star analyzer. Well, as it turns out, many compact comets are compact enough that you can. Here's another example of our most recent NEO-Ys, and you can see here we're detecting the sodium. Pretty cool, huh? So anybody who uses a C-clamp in their setup, that's my kind of observer. Now, if it was me, the problem is I would crank that C-clamp down so tight I would buckle the housing and destroy my video camera. But Robin Leadbeater is a much better observer than that. He put a star analyzer on the nose piece, and this is down at the bottom is a single frame from a video he shot. And you can see right around here was a little bit of an outburst, a bolide. But you don't need a bolide to observe. You can just use the spectrum. And terrible arrow there, but there you can see some of the minerals that he detected in that spectrum. And this is a little more esoteric than just off-the-shelf spectroscopy. You got to be lucky, and it's a little tricky, but it floats some people's boats, so cool. We're not going to talk a lot about the sun. We've heard a lot about it over the last 2 years, and will again in 2 years, except to point out that we discovered helium on the sun before we discovered it here on Earth. It's an amazing story, a great example of science in operation. And again, the reason we can use a slitless grating on the sun during an eclipse is because it becomes just a narrow sliver instead of this big extended object. So if you have even a DSLR can detect the differences in variable stars. That one has some iron in it, that one doesn't. Again, brief review of Doppler shift. Yeah, and many of you have explained it and probably do a better job than I do, so forgive me. So Doppler shift is the change in pitch or color that a wave goes through if it's coming towards us or moving away from us. The common example is a train whistle going through a station you're standing in. It's right, high, low, high as it's coming towards you, low as it's going away. Same thing with light. So suppose we were expecting to see a spectrum right there, but instead we saw it there. That's redshifted, and that's Doppler shift. We can actually measure the speed that that star or galaxy is moving away from us by measuring that redshift. Suppose the spectrum is shifted in the other direction. That's blue shift. Same thing, we can measure how fast the thing is coming towards us. Here's a great example, a supernova. We're not going to talk a lot about supernovae, but again, this particular type 1A supernova involves two stars. One's a white dwarf, and some of the gas from the accompanying star ends up on the white dwarf, and when you throw gas on something hot, you get an explosion. Let's take a look. So there it is in M101, a supernova. There's an image of a similar type 1A supernova, not this one. Notice that it looks spherical. It doesn't just look like a disk. You can actually see that it's got some structure. You can even see through it some of the stars that are, I suppose, in the background. They could be foreground stars, I suppose. So David Strange, with a 9-inch celestron and less than 15 minutes worth of imaging time, captured this spectrum, and he was able to see that very deep dip. Now, you all know that we're standing on the shoulders of giants. And the giants have determined that there are different types of supernovae. Some involve two stars, like I talked about a moment ago. Some are just the star collapsing on itself, a core collapse. And they have different fingerprints in spectrum. Here's a great chart that shows that. So on type 1A supernova, that deep dip there is ionized silicon. And it's what, at about 6,000 angstroms. These core collapse supernovae, and there's several different types, they don't have, if any, a very deep Illinois, I don't know where that came from. Ionized, that's where it came from. Ionized silicon dip. So now we can use that to determine this is a type 1A supernova, and that's how professionals do it. Now here's a cool thing that David did. He noted the wavelength that he observed there on the x-axis. It was 6150 angstroms. So he plugged it in there. Then he looked at what the wavelength would be if Bunsen had burnt beach sand, stationary. Those numbers are different, right? So when I couldn't remember the Doppler shift formula, again, Wikipedia is your friend. There's the numbers plugged in. Wow. So there should be 3 wows there. This is the blue shift of that supernova shell as it's coming towards us. My watch is telling me it's time to stand up. I think I'll defer that for a while. So it's the first wow is I can't believe I could observe that in less than 15 minutes of imaging time with such a small telescope. The second wow is, wow, that's fast. The third is, wow, I'm glad we're so far away that even though that's fast, it's never going to reach us. Now, some of you may be familiar with Adam Rees, who won the Nobel Prize a few years ago for work that he and his team did just before the turn of the century. They studied the cosmological accelerating expansion, and they used type 1A supernovae as standard candles in that process. So, somehow I think their equipment was a little more sophisticated than this. But bang for your buck, you can't beat a $200 grating. You really can't. I mean, he figured he was using $1 million telescopes, right? So how about the spectrum of a black hole? Now, of course, a black hole is black, and doesn't have any light coming out of it, except the matter that's circulating around it, that's rotating around it, is going so fast as it spirals in that it does emit light. So David Hayworth in Oregon, Portland, Oregon, just south of me here in Seattle, observed 3C273, and there's the spectrum, 2 little dots showing up in the spectrum. There it is blown up. And there's the spectrum itself, profile, the graph, the intensity graph. So in 1965, this guy was in his mid-20s, Martin Schmidt. He looked at this and was really pulling his hair. And the reason I know this story is because there's a wonderful transcript of him being interviewed as he describes his discovery. And it's wonderful because it describes the science and the personal side, because he could not figure out what this was. And he decided to go back to basics, to identify these peaks. He said, first of all, let me eliminate those being hydrogen. We know hydrogen's everywhere, but no, they aren't hydrogen. And so he brought up the Bomber series. That's the one I asked you to keep in your mind's eye, right? And you can see those blue lines indicating I need to go in the right direction for your view, which is that way. You'd think I'd get it right eventually. The problem is the preview window a speaker sees of themselves, and you see of yourselves in video on Zoom, is a mirror image, so it's not confusing to you as you're looking at yourself. So I'm looking at a mirror image instead of the image that you all see. But regardless, he looked at those lines, and he said, well, above this hydrogen alpha line, there's no big peak, and there's really no big peak. There's no pattern here. So it's not hydrogen Bomber series. At least he figured that out. He could move on. except it was, and he didn't move on. He figured it out. It's the hydrogen bomber series redshifted an enormous amount. Well, that meant this object was an enormous distance away using the Hubble constant. So the discovery wasn't that it was that far away, but it was that it was that far away and so bright that we could see it. That meant intrinsically, 2 billion light years away, it had to be freaking bright. And it was. So as amateurs, this was done with a modified security camera, not some expensive cooled Fitz camera and an 8-inch SCT. With the Hubble constant, we can calculate the distance or the speed, the recession speed of this object. To me, what's amazing is this spectrum, this light, has information in it that has come that distance, 2 billion light years, over such an enormous amount of time, and yet there's still very clear information in it that we can extract. It's remarkable, and nothing that I know of in the universe ages quite as well as that. Certainly, here's Martin Schmidt a few years ago. He's a little different now. Now, I'm aware I'm throwing rocks in a glass house, right? So he's got a full head of hair. I'm actually jealous of him. So 2 more examples and we'll finish up. So far, we've been looking at the hydrogen alpha series mostly, because those are really strong lines, easy to find. And how wide are those? Let's just take a look here. What I'm going to do is just drop a line from either edge of these. Ooh, that wasn't the line I wanted to drop, but this is. Drop a line down to the bottom here. There's one edge. There's the other. So let's see, that's 20, 40, 60, 80, 100. So this is about 20 angstroms wide. And we can see it's our resolution's a little better than 50 angstroms, but not much better. I mean, we couldn't observe a spectrum of we couldn't actually separate it if it was that narrow. That would be a little more smooth than my drawing. What if we wanted to drill down and look at the details inside of one of these features? Then you need a more expensive spectrograph, one of those Slit devices, to get the added resolution. Almost no one, I think 1 in 100 or 1 in 200 or 300, starts with a Slit spectrometer because it's a big step financially in terms of commitment and learning curve especially. So, but what we typically do with spectra and science in general is we display a known object and our unknown or target object, and we compare them and look for similarities and differences. So let's compare the moon to Vega in high resolution. Well, you can see that their dips are in a different position. The moon is relatively stationary to us, right? It's not really moving appreciably towards or away. But clearly Vega in fuchsia here is offset from it. And from that offset, we can use the Doppler shift formula to measure the radial velocity fairly accurately in a quick image like this from the published value. So notice though that this is at sub-angstrom resolution. So we'd have to get down to like 0.7 angstroms, 0.7 angstroms wide there. So clearly a star analyzer without a slit won't work. So my final example here, I have a little visual help here. This is a rotating star. It's rotating very quickly. And so this edge is coming towards you, right? My hand's getting closer to you. So the light coming off that edge is compressed a little bit as if, so that is blue shifted. Whereas this hand, as the star rotates, is moving away from you. So that's red shifted as that light moves away. Whereas the light here isn't really affected. Its distance to us isn't really affected by that rotational speed. So what happens is, last example here, is some of the light that should be on this peak is actually Doppler shifted into the blue. And some of the light that should be here on the right is Doppler shifted into the red. And here's what it looks like. So in blue is the star, it's Altair in this case, rapidly spinning. So some of that light that I mentioned earlier has been stolen as if by Doppler shift into the wings here. So now we can study Doppler shift. This is a slit spectrometer, but this is the kind of research, about 80% of the research that gets done in spectroscopy or in astronomy is done with spectroscopy. Now, I missed my cue a little earlier. My wife always says I should dress for success. And so this is what I've been using. You can see there's the hydrogen alpha line. I think it's right in there if you've got the resolution for it. And it's a little messy here. I want to apologize, and maybe my salon's just not answering their calls. It's just a problem. And not only is it a mess, but if you look down in the roots here, there's a lot of gray going on down there. I know some of you have seen this at home, the same kind of thing. That gray is just not doing it for me. So let's finish up here, talk about how to get started. A grading, number one. Second thing is almost any camera, as I said, monocolor, cooled, whatever, video still. You may need an adapter or a spacer, and that's because this distance isn't critical, but it needs to be in a certain range. And that's because if it's too far away, then the light has too much time to spread out and it's larger than your sensor and too dim. Whereas if it's too close, the light doesn't have enough time to spread out, and so you don't get the resolution or the dispersion you need to actually see those dips or those peaks. And finally, you need the software. So there's a lot of good and well-tested and well-known high-end software out there that's free. I and others have run into problems with it. That's why I wrote RSpec. So one of the obstacles to getting involved, as I mentioned, is how do you know what you're looking at? Well, those books you're seeing on the screen, I wanted to show you 2 pages in this book because it's got these wonderful examples. I don't know if that's blurry or not at that distance, but it's got these wonderful examples with call outs, which frankly, for an idiot like me, isn't enough. Who cares if there's nitrogen and oxygen? I don't know what that means. I literally don't. I'm not playing dumb here. It's my natural state. But the cool thing about this book is it's got a lot of accompanying prose and explains to you. So I meant to mention this earlier. If you're not an imager, who cares? Still, spectroscopy is an important enough field that hopefully from this talk tonight, you've gotten a better sense for it. And you could even use my software for free for 30 days. You could download it tonight or tomorrow morning. It's free for 30 days, and there's tutorial videos, including a 1-hour workshop I gave in person a few years ago to the AAVSO. And in that workshop, and the sample data is downloadable too from the same place, I walk through how a spectrum gets processed. So even if you never plan to capture a spectrum, if you want to have some fun, maybe you have a little bit of free time on your hands this year, that might be something you could do. So AVSO, as you saw back there, they're getting more involved. I'm giving a talk later this month to them, as well as a workshop and a couple talks to their, the workshop later this month is free. You might go check it out. There's a really good video series or workshop series that they're doing with a variety of topics. This one's on the 22nd. And you'll see a lot of the same things I'm showing here tonight. So there is an opportunity for pro-am collaboration. Most of the names there in the author block are amateurs. So we've come a long way in the last 55 minutes, 50 minutes or so. And we've also come a long way in the last several hundred years. Fraunhofer, as I mentioned, is credited with inventing the spectrometer and seeing the first star spectra. Kirchhoff was a friend of Bunsen's, who gave us some of the theory to explain emission versus absorption lines. I want to finish up with a quick story. Forgive me for going a little bit long tonight. I was down at Pike Place Market 6-7 years ago. I had a Lunt telescope for solar observing. I set up, I immediately got shooed away by, in fact, I'm going to stop sharing my screen at this point. I got shooed away by the Pike Place Market police who said I needed a busker's license, even though I wasn't charging anything. So I went across the street and I was observing there. And also there were some street people, not people who slept on the street, people who were just hanging out. Made me a little uncomfortable, which is my small-mindedness probably. But at one point near the end, one of them came up to me and said, "Can I take a look?" And I thought, yeah, he's not going to get much out of this, but sure. I said, sure, happily. And he looked and he asked a question or two, and I'm doing the same spiel you all do, you know, prominences, sunspots, size of the earth, all that stuff. And then he turned to me and he looked up at me from the observing chair and he said, "How did you learn all this?" And at that moment, the gap between his and my life and opportunities really was evident. And the reason I tell that story is because I want to thank all of you who are doing outreach, because I think it is the most important thing we can do. The fact that you're here tonight and interested in this indicates you did have opportunities that you took advantage of. And a lot of people don't. And by doing outreach, you can share some of the opportunities that you have. Again, I'd like to thank you all tonight. I'm available for Q&A until we run out of questions or you guys hang up on me. And I'm always available on the web with a contact form on our site. Thanks again.
Thank you, Tom. We really appreciate it. It was a great talk. We did have one question during the talk
Okay.
that I want to forward to here from the chat. I think you covered it a little bit with some of the images you had, but it asks, if you're looking at something in the sky, how do you know you're looking at one gas and not a combination of gases? So when
That's
you're
a
looking
good
at the
question.
spectrum, yeah, how do you not separate the overlap and things like that?
That's a great question. Let me share my screen just really quickly here, and we may do this a few times during the Q&A. And let me just jump to a particular slide I want to show you. Oh, there it is. Let's see if I can do it here. It is slide 18. Oh, that's how you capture the spectrum of the sun, by the way. So what the questioner is asking is, suppose two stars or two different elements have a line in exactly the same position. So if the star has helium, and maybe this line on titanium is in the same position. You can't differentiate them. In fact, the devil's in the details. Actually identifying the elements can be a big challenge. And so oftentimes what we do as amateurs when we're beginning is we capture spectrum. We more or less know what we're looking for from a book like this or from talking with people. Other than that, there's no easy way, except that most spectra at a higher resolution, you don't have those kinds of overlapping lines. So you're able to differentiate. But it is a little bit of a challenge sometimes if you've got a lot of lines. For example, with the solar spectrum, there's so many lines because it's so bright. In fact, I wanted to mention that since I was talking about brightness. Why should the solar spectrum be any more complex than any other star? Well, it's because it's bright. So the question that gets asked is, how dim a star can I image? So normally when you image stars, just real quick, normally when you image stars, depending on your focal length and your pixel size, your photons are falling on a handful of pixels on your camera. But now with the grating, you're picking off a whole bunch of photons. Same total number are there, but you're taking some and you're spreading them out onto the sensors. Now you've spread the same number of photons across hundreds of pixels. You lose 5 or 6 magnitudes. So if normally you can image down to magnitude 15, you'll be able to image down to magnitude 9 or 10. There's tons of stars to observe. But with the sun, it's so bright that we can see details just like other objects that we can't see with other objects. So I hope that answered your question. I'll stop the screen sharing again.
Yeah, that was great. Thank you. There's one more question that was asked. And also I want to say, if anyone wants to ask their question directly, you can unmute yourself and do that if you'd like to. But first, I'm going to ask this one from the chat. And that was, at the beginning of your talk, you said that spectroscopy represents the 5th dimension. What did you mean by that?
Simply, and I used air quotes around it because, first we have just visual imaging, and then we have, the 2nd dimension of distance during eclipses, and then the 3rd dimension is time when things are going on and off. And I forget what the next dimension was, but it's just a different way of extracting information from starlight. So it's not really a 5th dimension in the pure physics or cosmology sense. I'm sorry if that was misleading. What else?
There are no more questions in the chat. And
yeah, I have a question.
Oh, Tony, go ahead.
Hi, Tony.
Yeah.
Thank you.
Yeah, hi. Thank you for your talk. Very, very educational. I sometimes build some of my own equipment, and I'm wondering if you have any recommended sources for diffraction grading, and also what would be a good blaze angle to choose for grading.
That's a good question. I don't know. The vendors, I forget the name. Oh yeah, of course. Edmund Scientific is one.
Mm-hmm.
I forget what the blaze. I actually don't remember the blaze angle on
Sure.
these, but that's an important thing to know. The other thing is, you're going to spend a fair amount of money before you're done. This is actually, or the star analyzer is the grading is sandwiched between 2 pieces of astronomical glass and then mounted here. I'd ask on our forum, if you just Google RSpec or email me off our contact form.
Sure.
The guys in the forum and women in the forum too know a lot more than I do about the hardware issues. And they build, lots of people build things. And so they'll know a lot more about the hardware. It's a good question. It'll be a fun project. The other thing is the do-it-yourself 3D printed device is called LowSpec, LOWSPEC. And is it Thingiverse? Is that where I think the plans are? And I think its parts list would probably indicate the grading that you need. It's a neat project. It might be a little tricky because it is a lot of optics and important angles and things. But I'd love to hear what you end up doing if you do it. I'm glad to hear you're thinking about that.
Oh, okay, thank you.
Sure, you're welcome. Any other questions? Okay then, listen, thank you all again. Thanks for the outreach you do. And when we can start doing it again, I hope you'll continue it. And have a nice evening. I'll get out of here and let you talk behind my back and carry on. Thanks for laughing at my jokes. I saw some nice smiles there while I was talking. So see you all later.
Thank you so much, Tom,
my pleasure. Jim,
helping
thanks.
us
I'm glad
out.
we got you in and you were able to see it. That was important to me.
Sorry about that, but all's well that ends well. Great
Exactly.
talk. Thank
Well
you.
said. All right. See you all later. Good night.